Word up. Nationwide hated. Nickel plate.
Sequel or death? Yo, son, what are you going to choose? Yo, check it. This seminar is filmed at Carnegie Mellon University. Thanks a lot, Google.
This is it. We're super excited today to have the Monty Widenius, the creator of MySQL, MariaDB, and I've since learned not the creator of MaxDB, but the namer of it. Monty has been super well known in databases for the last 30 years. His contributions to the open source community are massively significant. So there's not much else you can say. Just go read the Wikipedia article about him and see how awesome he is. So we appreciate Monty giving this talk because it's currently almost midnight in Finland where he's speaking. So again, we appreciate him staying up late to talk about MariaDB. So as always, if you have any questions for Monty, feel free to interrupt at any time during the talk, say who you are and where you're coming from. And that way he's not talking to himself for an hour over Zoom. Okay?
It's
What?
me, Monica. I'm your long lost daughter. I haven't seen you basically since I was born.
Wait, who's this?
I'm Monica. Apparently I'm Monty's estranged daughter. That's what my mom told me, and I'm in America. Dad, I miss you. And how come you won't name a database after me?
Maybe
Wait.
because I didn't know that you exist.
Wait, Monty, do you have a fourth daughter?
Nope.
Are you sure?
Not as far as I know.
Are you sure?
And especially not as far as my wife knows.
Okay. All right. Okay. I don't know what this is. I mean, it'd be amazing because you could name a fourth database after after Monica, right? Are you here to announce this now or no? Is this a real person?
But then I would need to do a fork again, and
Okay.
that would be quite painful.
Okay. All right. Well, I don't know who the person is. I'll just mute them. Sorry about that. How do I get rid of them? Remove. Done. All right. Sorry. Monty, the floor is yours. Ignore that. Thank you for being here.
Okay, so I'm here to talk about the MariaDB optimizer and a little bit about the background. So we will have a couple of history slides about where everything came from. So I've been working with databases since 1981, probably before some of you were born. And I started by creating an application where you just paint things on the screen, and then you automatically can start putting in data, and you could also do reports similar ways. This allowed you to create something like a bookkeeping application in a couple of days compared to months back then. And back then, there were no optimizer. Because when you did the report, you said that first this table and it's linked to this table and this linked to that. So everything was predefined. But I spent a lot of time on making scans very fast, making index retrieval really fast and specific rows. And there were lots of summary tables that was trivial to create with the tool. So we could give customers instant update when they asked, so in this gas station, which are the largest customers and what are they buying? We could give that in sub-seconds. And this was on a computer with just a few megs of memory. But so when I created then MySQL on top of the old part, creating an optimizer was the first big task because the storage and everything around it was already done. So the first version was created on a 32-bit computer. And then a couple later, I started to move to Unix and C. And that was created on a 4 meg Spark computer, who was then eventually getting 60 meg and so on. But that also, when you start working on something that is only 32K, you start to be very cautious with your memory usage. So many of the algorithms in MariaDB uses very little memory. For example, I created a way to do hashing with no extra room. So if you have a hash table with 10 entries, you have the hashing will take 10 entries. There's no extra need for duplicates values or doing that. And that's still used in MariaDB today. So from many point of view, MariaDB is and MySQL was a practical database. I didn't know so much about SQL back then when I started. I did know the basic, but we had the philosophy that everything we do is to make it easier for users. We try to do follow the SQL standard, but if the SQL standard was too inflexible or there were a better way to do that that was not in conflict with standard, we just added that. So this makes MariaDB a little bit different. And also from Unireg, we had the concept of different storage engines and for different purposes. And the reason for that was that I started by creating Unireg with something called CISAM from a Swedish company. And then the company said some years later, oh, we are not stopping supporting it. So I created my own version of CISAM with, we call it then MyISAM, but had more compression, more options. But I didn't want the customers to, if they upgraded to new version of Unireg, I didn't want them to have to change all the tables to the new one because customers people hate upgrades. So in this case, they could just use the old engine, and if they wanted the better performance and options, they could just switch engines. So that was kind of the beginning of the storage engines that we have in MySQL and MariaDB. So the optimizer was first created by me from scratch, and I had never written an optimizer. I had read about some about databases in the university, but they were very basic. They were more about how to use distributed databases. So we have one table on this server and one table on this server, and how to do joins about that. But it was not practical for what people needed on the internet. And most of our early customers were using OLTP, and with lots of connections because MariaDB, actually MySQL, was the first program I ever created who were using threads. And because I wanted to have or be able to support 10,000 users, which we can do. So we had lots of optimization for basic queries. We always assumed in the beginning that good indexes should exist. And we have a hash join, but that is kind of used only when the user has not defined indexes that should be there. So that was kind of the beginning. We do have lots of optimizations that were added later. We had optimization team who actually had studied databases in the university, and they did add functionality that we didn't have in the beginning. But the beginning was just get the problem solved good enough and take shortcut if it makes sense, but don't take shortcut that would stop us from doing things, let's say, call it properly in this case, in the end. So we did add, for example, subqueries only come in MySQL 4.0. That was around 2000, and the first MySQL version was in beginning of 96.
So would you say the first version of the query optimizer was a bunch of like if then else statements? Like if you see a pattern, do this optimization?
No, it had subqueries. We didn't have subqueries until around 2000. So we have the first.
But I'm saying like the initial version you guys wrote, it was like rule based, if then else, or if then apply this rule, and then I understand.
No. So Unireg was rule based. So
okay.
when we created, I created MySQL, we did the full optimization, we did analysis, we had cost, but it was still optimized for that we have indexes. We could work without indexes, but we didn't have hash join in the beginning, so we did basically a full loop over all combinations.
Thanks.
So what I will talk about in this talk about something that makes MariaDB still unique as far as we know, in this case, me and the Optimizer team, compared to other databases. I don't know if they are unique because I haven't looked what every other database supports, but I think some of those should be interested to the audience, and I will go through those in the hope that that will be true. First, a little bit about how MariaDB is orientated. So this is a slide from a full optimizer talk with regarding InnoDB, but the important thing is here that is the storage engines. What makes MariaDB unique is that we can have the storage is decoupled from the parser and the optimizer and everything else, and you can have different engines. Both things that are totally in memory, like the memory engine, or InnoDB with the clustered index and fully transactional, an area, and MyAsam, who is not transactional but has a very low footprint and uses much less disk space. And then we have S3, who allows you to store data in S3 storage, with high compression. But the storage engines is important for the last part of the talk. So first of view about the optimizer, which this talk is about. I don't expect that this is anything very different from other ones, except maybe the constant tables and the range. So I will go through those in quite a lot of detail. And the difference between data independent rewrites and data aware writes is that MariaDB is very good at using constant for finding out what's the best plan. And the data independent rewrites is rewrites that we do without looking at any data in the tables. For example, if you have A equals 5 and B equals A, we know that B also will be 5. So we do that in the first pair. But then come the constant tables and the range analysis, where we do data aware rewrites and do decisions based on that. And also, this I will not talk about this, but just to make it clear that our optimizer is nowadays state of the art, and we have a lot of things that is probably the same thing as you can find in any other competent SQL database. This is just to show that we have a lot of different optimization for subqueries, among other things. Yeah, this is mostly because I showing this because I heard some people in the Postgres community saying that MySQL and MariaDB is just a toy. We don't have proper optimization. It just shows that we do have most of those that you would expect, and probably more. In some areas, less in others. And that's true for any database.
If it makes you feel better, Postgres's subquery rewriting is terrible too.
Yeah.
Yeah.
Okay. Let me. I want to get to fix one thing on it. Okay. So first, the constant tables. So constant tables comes in two forms. One is that if there's a table who has only one row, then we will read it at the beginning of the optimization and use that, all that columns and constants. This allows you to basically drive an application by having one constant table who has some rules that you can use. And that's quite useful instead of having to have those in all queries. That's one part. And if you have, in this case, T1 unique key is 1, 2, 3, 4. So we do know that this T1 will only have one row. So we read it early, and then we use T1 and all columns like they would be constant. So this allows us to do a lot of interesting things, especially the opt-range optimizer part that I will go through.
Just to be clear, so the optimizer starts planning. It sees that you have this kind of setup where something equals something, and you have the constant. So then the optimizer basically stops. You make a call to the execution engine or the storage engine that corresponds to wherever this data is. You go fetch that one row, which could be an index lookup, presumably.
It is a unique key. Of course, this index lookup, yes.
But so then you come back with that row, and then now you're filling in that constant. And then do you have a way to pass along the context? Like in this case, you're doing a join. If you need the columns for that first row you fetched, that's retained.
We basically replace everything everywhere in the where class and other places the data from the row as a constant and treat it as a constant.
Got it. So I think we had somebody from the Oracle team, MySQL, gave a talk about how you guys do this 5 years ago, and this is bizarre. Like I don't think anybody does this. It's super fascinating.
Yeah, and it actually helps because often you're searching for one customer or everything else, and suddenly you can use that to do more things. And the thing is also that it's not good for prepared statements because if you have the unique key, or you have for example, T2 call can also be unique. But if there's lots of values there, the plan changes. MariaDB is really good because of this and the range optimizer to do replanning based on data that is in the database. I will come to that. Okay. And that's the range optimizer. And this was something that I created already in Unireg. So the code is basically around from 82, 83, and we're still using that. So the idea is that if you have constants that are, for example, in this case, you have a depth and you do support sales and you have a higher date between something. We will create for this basic range a set of ranges, and if you can see on the right side there we have sales, and there are basically two ranges in sales. We need to find all rows of those, and also for the support. So we search this live at the beginning of the optimizer, and this tells us quite with high precision how many rows are they in this complex range. And if it can be actually pretty large, because you can also we have users who does for example the depth in and then thousand ranges. In this case we will cut the tree to make it smaller. So overlapping ranges are joined together. We guarantee that no range will be the other ones. So in this case, we have to only to fetch the rows. We start with the first range, the first value. We do read next until the end, and then we do it for all ranges. And then we have all the values for that without having to do any larger scans or anything else. We only touch those rows who actually are in the set. And we can handle this for all the normal things. Bigger than, less than, between, like with a star and everything else.
Presumably these
and then I will just go to the estimate, then you can ask questions. So how we have a set of ranges. So how do we get the rows? So basically what we do is we take the beginning range, and we do a dive into the B tree, like you can see on the right, and then we take the largest base value and do a dive, and we basically see that in which % of the B tree are we in this, and that's pretty easy to calculate. This gives us, for any range, a reasonable estimate, much better than any statistics or, let's see, what's the word?
Sketches and summaries.
Yeah. But it's precise, and this gives us a good, for any table, it gives a good estimate of how many rows will we do that. We may not use this, the range as the index, because there may be a better one, but we have a top limit of how many rows we are gonna fetch, which allows the optimizer to do much better job. And this works for both single column and multi-column. So you had some question, Andy.
Just to be clear, so you first check the histogram, like you break up the range.
No, we don't use histogram at all for this.
Sorry, I meant index.
We treat it as a big histogram with much more exact.
Yes, I misspoke. So first you break up the ranges, and then you probe the index to see what percentage is going to be covered. And then that gives you, that's how you're getting the selectivity estimates for a given index.
Yes. Or where in this case, you have a index on index depth higher date. So that will tell us that for this total number of ranges, there may be 100 rows or something like that.
And then for every potential index that would satisfy this query, you do the same thing for all of them.
Yes, for every index, for every table.
And then I guess my question is also to, like, presumably the probes in the index have to be transactional. So like they're running in the same transaction context as the original query. Because technically you haven't started running the query, which you kind of are.
We start the transaction context for the first dive we do. For example, if we do a constant table, we have to ensure that that is in the same transactional context. So everything is in there. But the thing is also, these are estimates. It doesn't really matter if they are exact or not. They have to be just better than anything else, because we are comparing those to other ones. But for example, they may, in this range, there may be rows that has not yet been committed. We don't care, because it's an estimate. Mm-hmm. And any statistics or histogram is also estimate.
Have you guys measured to see how, I mean, there's a computational cost of obviously probing the index. You take latches as you go down. And if you measured like the sort of the performance and accuracy trade-offs between a traditional histogram or a sketch or something, using like traditional methods to estimate these ranges?
So usually we are within 10% of the real value, which you can't get histogram. The worst case you have, if you have when you insert, the tree can be balanced on the wrong end. In that case, if you get a dive there, then you can be 40% off. But even that is a good estimate for choosing the right index.
And then for certain storage engines, like the B plus tree, well, if it's MariaDB, the primary key, the leaf nodes is the data, so that makes them kind of expensive to read, I suppose. This works both for the primary index and the secondary index. Usually, less used with the primary index, because usually it's that you try to keep those short. Got it. Okay, awesome. Thank you. And the one challenge with the multi-column index is that if you have Finland and engineering, those, and you have index on both and those combined. So then the question, what's the selectivity on those? And I have a slide for that. Is that assuming that you have indexes on call 1, call 3, okay, it's listed down there. The thing is that now you have statistics that overlap. So if you try to do statistic to get the selectivity of this table, you can't just combine those and for example, what you usually do, you believe they are independent, and then you just take the selectivity of each expression and multiply that with others. It doesn't do that. It doesn't work.
So what we do in MariaDB is that we start with the index which has the least rows, and then we skip anything else that is using the same columns, just to not get the selectivity wrong. But if these are 3 indexes, we will then normally scan the index with the least amount of rows. But you still want to know when you apply the where clause, how much less will the selectivity be. So this is just a couple of things that we do. That is and for any optimizer, you need a way to actually see what the optimizer, how it works, which plan it's skipping, and all the costs. So we added optimizer trace some years ago, which is a output is JSON to make it easy to read, and it's good for troubleshooting. But also that the old optimizer in MySQL was kind of primitive in the way that one cost was one disk access, and we also assumed that one key lookup is one disk access, and everything is one disk access, and except for a couple of things that was a little bit less, but not much. And we had a hard time changing that because we needed a tool to be able to see, are our plans actually better? So when optimizer traces was added some 5-6 years in MariaDB, that opened the opportunity to create a new optimizer, which I did in my MariaDB 11.0. But I will come to that later. So what we notice when with an optimizer is that you have something that is pretty good for normal cases, but customers and users very often doesn't have normal cases, and they just expect things to work. So we have cases where we have column in and 50K of values, and with the range optimizer, we're trying to find all ranges. If you add that with some and some ors, you suddenly have ranges that is gigabytes, and that doesn't work in practice. So we have to cut those. And we also see a lot of users who have lots of and or all levels with lots of constants, but then we try to build the ranges. It becomes more expensive to create them and ask for the statistics than actually just execute it. But these are exceptions. In general, the range optimizer works really, really well, and we have seen that when we take practical applications, so that people are converting from Oracle to MariaDB, the range optimizer fixes many of the queries. But then you also have users who just expect that you do a year on a column, and that should be used an index. So we added that, but we added that I think a year ago. And the same thing with uppercase on a customer name. That is also something that index can do, but because most of our index is case insensitive, but we still have to notice that upper is a special function that you have to handle. And there is also optimizations that is based on that you have very little values in the group by. You have to detect that, and then you have to do special optimizations for that cases. Lateral derivative optimizations also exist in other databases, but that was something that we didn't expect in the original version of MariaDB. And of course, even if users are doing things that they shouldn't do, using tables without indexes, or using indexes but have different collations, or just bad schema designs, you have to be able to support that. I remember a year 2000 I think it was something similar to the Super Bowl, but in England. But and they were running a full application with MySQL back then, with lots of data, lots of tables, and then they were asking us, could we come and help them optimize things, because they were able to execute the event, but they noticed a little bit of delays, and they didn't have a single index on a single table. So, but they were not complaining about the speed. They were just wondering, can we optimize something? And we did. Okay. So I did touch on the new optimizer in MariaDB 11, and that was only possible thanks to the optimizer trace. So the redesign, or the big redesign, was that we changed that one optimizer cost is, instead of an IU, it's 1 millisecond. So I have gone through all storage engines and different parts of the server, done performance analysis, everything else, and calculated what the timing of each small unit of work, and then put that in all parts of the server. And what makes it harder for us to do this in MariaDB is because of the different storage engines, because they are different. And we also made it possible for tuning the disk access, and each individual engine can be tuned. But of course, there's some things that you can't predict. If you have something like column-like percent foo, you can't know how many rows will actually be fetched, or will be accepted by the where clause. So there are always something that you can't tune.
Can you go back to the previous slide? So you're saying one more. So you're saying that. Sorry, go back one more slide. Yeah. So you're saying that instead of doing your cost estimations on disk I/O, you're basically now accounting for all of the computational costs in addition to disk I/O, and yes. and you're sort of chunking up. Like if I sort 1,000 tuples, that's going to cost 1 millisecond. So you sort of manually went through the system and said, if I do this amount of work, it's going to cost 1 millisecond. And then now in your cost model, you're saying, okay, to run this query plan, here's how many times I'm going to invoke the sort, the row ID filter, and that's your cost estimate.
Yep.
Okay, impressive.
And this comes just from the fact that when we started in the beginning, we did things easy. The one optimizer cost actually worked pretty well, but there's always a case when you have to decide, should I use this index or should I use a table scan for doing that? And usually if you have to access more than 20% of the rows, then the index scan is faster. But we didn't know that before. And so previously we were using index scans, or scanning the index instead of doing table scan in some cases. But that's always a slow query, so people didn't notice that. But still, there are always cases where that caused a problem, and 11.0 and above should fix it.
But this also means too, like the code base becomes somewhat brittle, right? Because now, say you change the sorting algorithm, and what went from, say, 1,000 tuples takes 1 millisecond. Now you can go 10,000 tuples 1 millisecond. Someone has to then go update the cost model to somehow reflect that change, right?
Let's say most of the sorting is still retrieving the rows from the table, putting them in a sort, and then the sort is basically file-based. So we're calculating all that, and it's reasonable exact.
And you say calculate, you're manually calculating, or somehow the code can update itself or runs its own internal tests?
So I have a script that is included in MariaDB that helps you calculate all the basic primitives that we have, and I will go through those in the coming slides.
All right, thank you.
But what makes things complex for us is that we have InnoDB with a cluster index. That means that primary key access are faster than anything else, including other databases, just because you get the row data. You don't need to do a extra fetch for the row. But that also means that secondary indexes are slower, because when you access the row data, you have to go through the key in the secondary index and do a search in the primary key to get the row. And then you have B-trees with pointers like MyISAM, where we point directly to a file, and this is basically a file on disk, so the disk position. So in this case, MyISAM uses the file cache for the data, not for the index. And then we have area, which is like a modern version of MyISAM that you can have run both in a pointer in the to data like MyISAM, but also have things in a that is cached in memory, and we don't depend on the file system. And then we have the memory engine that supports both hashing, which is the default, and binary trees, and all those has different costs, and all of those we have calculated. And then we also have a problem or possible problems with when you go to remote storage. S3, you have to do a HTTP request to get the data, and we also have federated engine like that can access remote MariaDB MySQL, and connect can go through JDBC. So the three last ones are not fully cost-based, so they are rudimentary, but all the other ones are done in detail. So what we calculated. So I basically looked at how the engines are working, and spread things to about 10, actually 12 variables. So you have the key lookup. That means that we find the entry in the index, and in this case, DB has for clustered keys has a total different cost than in not cluster keys. And then you have key next, which means that when we have find the first key, and then we do a key next, usually that is cached by the engine, so it doesn't have to do a full B-tree access. It just goes and find the next on the page. So that's much, much faster. So if you, for example, are doing what we call a ref access on a key, and we know that it's 5 rows. So in that case, they will have a cost of a key lookup of 1 plus 4 key next. So we also have key copy and row copy. Key copy is copying a value of the key, because we can do key read only keys, that we call them, and so we basically get the data from the key. We don't have to go and fetch the row. And if we have the row, then we need to copy the row, which is much more costly than a key, because it has more data. And then we also have row next, finding the next row. And the index block copy is that when you do go through a B tree that is page oriented, getting to one index block and then go to the next, you usually have to copy the last block and save it so that you can do index next. So we also have calculated the cost of doing this one block copy that is needed. And with that as a base, the optimizer goes through all combinations of tables, looks at all the different indexes, and checks if rain key can be used, cluster key, calculates the cost for all the combinations, and for each table it uses the one with the least cost. But we also use the data from the other possible accesses to define what's the max amount of rows that we have to cover. Because if we have a clustered key that's really, really fast, that may have 1,000 entries, but the range key tells us that there are actually only 500 entries. Then we know that when we go to the clustered keys, we will only find 500 entries that will be satisfied the where clause. because the range tells us that. So we can use that to provide a better estimate of both which keys to use and how many rows we will find. And last, I will not repeat that one. The basic shows that how we calculate the cost of one lookup in the clustered index, where we are only searching for part of the key. So that means that there is more than one row that we will find. So it's but this will give us a really good estimate, and we have tests to prove that that is roughly correct. And as we didn't estimate, it only had to be roughly correct. But the test was done with, I think I wrote it somewhere, that it was done with a table with kind of a normal order row that you can find in any kind of in a fact table with 1 million rows, and we took the data from here. And here you can just see the optimized cost comparing InnoDB with area, and you can see that the key lookup cost, it's much higher in InnoDB, and especially the row lookup cost is really high because it has to go through the cluster index, while area basically have a direct pointer to here's the page, and here on the page we will find the row.
You have results to show like that you're generating better query plans given these more accurate cost estimates?
Yes, we get much better plan in the 11 series.
Okay, thanks.
And all this data you can they are part in the information schema. You can actually change those. I don't think that anybody wants to change those, except maybe the cost of disk, because that is also a variable. We have a disk read and disk read ratio. Ratio is the chance of we have to go and find the cost, and disk read is basically milliseconds for reading a block. So you can basically optimize your database for your storage by changing one value. So things that MariaDB doesn't handle well is that the multi-start queries, where you have two fact tables that has lots and lots of rows, and then you have some connection in between. Because in this case, we can't easily go through the normal way that we work with a query. We start with one query, one table, and then we scan that one, and then find the next rows in the next table and get the other one. Because in this case, you basically should separate those and run two queries, and then should join those. So that's one optimization we don't have. But this is not frequent. I have had during the last 10 years one customer who needed this for one thing. So but every database had their limitations, and I wanted at least to acknowledge that we have at least one. Okay, and some reflections what we could do better. I think our prepared statement system could have been done better. We did some strange decisions, so that especially re-execution was really hard to get right. And we also did some changes regarding that. So we still have some old code there that doesn't do any harm but makes the code more complex.
Can you share like what were some of the bad design decisions you made for prepared statements?
So in the beginning, we wanted to make it easy to detect if a table had changes. For example, you have a prepared statement and you have done the optimization, and then somebody before the next execution does an alt that table. That code to try to reuse the old table, data, columns, and everything else when it was changing, and that was just way too complex. So we removed that some years ago, but there's still some fragments of that left. So that we should just clean up. It works, but we shouldn't have gone through several phases to make it right.
Would you say that's probably because the early versions of MySQL MariaDB, the catalog wasn't transactional? So like you would do alter table changes and you had no way within the context of that transaction for example, to invalidate prepared statements, because prepared statements were sort of stored separately.
No, we could invalidate them, but we basically, when we checked, when we started a new execution, has the table changed? But it was just done in the wrong way. That was too complex. Sometimes
awesome.
you do complex solution, and when you can't solve everything, and then you try to patch that until you notice that this doesn't work. So no, we have a much simpler method to doing that. And so the storage engine API is really good for handling different ways of storage. And when you look at databases, sooner or later, the performance of the database will be depending on how you store data. And having these different storage engines allows you to do both OLTP workload in a DB. You can have column store who can do analytical workload. But still you have the one server who is orchestrating everything. So for example, if you have two tables in column store, and then you have currently normally the upper level will try to fetch rows from both of those and do the join, instead of being able to tell column store that here's all the tables you need, do whatever you can, and then we do everything on the upper level. So we have an API for doing that, but it's not as smart and good as it could be. So we need to optimize that. So that was, I don't know how with time, I don't have a timer here. So what's the timing?
We have 12 minutes. That's fantastic. So let me first applaud on behalf of everyone. Monty, that talk was super fascinating, fantastic. I guess we have one question in the chat, but I've opened to the floor. If anybody else want to unmute yourself and ask Monty a question, feel free to go for it. First come, first serve.
Monty, this was great. I had a quick question on when you're looking at the table values to feed into the optimizer. Do you go and grab the read locks on the rows right up front before you start the optimization, or do you something else to not lock the tables early on?
So,
the rows of the table.
Yeah. So MariaDB is using MVCC, so we don't need to lock the rows. You basically, as soon as you access the table, you get a snapshot of the data as it is. So we don't need, there's no row locks at all. So MariaDB works by that if you do an update, we do an update in place, but we take the old copy and add that in the redo log. So you can access that. So that basically you can think of it that a versioning on insert. So read is painless, doesn't cost you anything, but except if you have to access a row that was changed, then you have to go and find it.
Great, thank you.
And area is using the same method.
All right, other questions?
May I ask a question?
Go for it.
On your slides, you showed that you invented subquery caching for multiple cases, but not for semi-joins. What is the reason? What's the problem with semi-join? Why you don't cache the results of semi-join?
So if you're talking about this one about subqueries, this one.
Yes, why only materialization here?
Oh yeah, but so we do have caching for on different levels for subqueries. So for example, if you have an in and a subquery, we do check that we cache every different value of in that was used. So if A in something and A is 1, 2, 3, we will cache values of 1, 2, 3 for the subquery, for example.
Yeah, of course, but why not semi-join? What's the problem? Semi-join have only multiplication, as I see here.
Semi-join in subqueries. If you use semi-join on the upper level, then there is you don't need cache because we will get the data direct from the table.
Okay, it's a bit strange. One more question about probing indexes. You said you probe indexes to estimate by histogram, estimate the size of.
It gives you the same result like a histogram, but more exact.
Yeah, sure. But in Postgres, we have such experience too. We have machinery to probe index during planning, and I personally tried to invent a probing index for equivalence operators, not only for inequivalence. And in both cases, as I see, we had multiple corner cases, which was painful for performance because you may touch a page which is on disk, not in the cache, and it reduces performance a lot. I guess I wonder, maybe you have some empirics which tell optimizer which time to use index, which time not to use index for optimization, how you avoid problems, performance problems.
Yeah, so this range optimizer, we have an upper limit that the user can define how many ranges we actually will probe. But if you have a query like this one, you probably want to have only those rows. And if you're going to use that index, fetching the data from the cache will actually be something that you have to do anyway. But this is useful for large tables, and the other option you have would basically be to scan the table. So which will be much, much worse. So we just see that it's very seldom where users have a problem with the range optimizer. It's only if you do an in with thousands of rows. And we actually have users who are doing primary key in and thousands of rows, and then they want to update. And they increase I think that we have a limit of 1,000 in the in, and they increase that to 10,000 because it's still faster than doing it any other way.
Okay, another question. You showed complex filters with multiple causes, and as I understand, you have some kind of statistics on multiple columns, and it's okay. It works in Postgres too. But what you do?
We don't have that because we just use the index. Because in this case, each dive here is on multiple columns.
Okay, I got it. But what you do with joins? My customers usually like join tables on 2, 3, 4 columns. So it's complex expressions. Do you have some tricks how to estimate join clauses when they consist of multiple expressions, ended expressions?
If it's first we see, can we use the index to do that, and we have used the index. If not, then we have histograms, and we also have general statistics. So for example, each index in both MariaDB and in most engines tell you how many values you have for each index part. So if you have a 3-part index, we know exactly, or statistically exactly, how many unique values we have on the first part of the index, and first and second part and third. So we use that also. And when things are not indexed, we are using histograms.
But you estimate join column by column, or you estimate them jointly?
Jointly.
Jointly. Oh, okay, interesting. And where I can read some paper on your algorithm, or it's closed source?
No, everything we do is open source. You can go to the source, or most of our algorithms are also described in the knowledge base at MariaDB.com.
Okay. One more question. Sorry, I have a lot of questions. Quite frequently right now, I see redundant queries because they generated automatically. They redundant, they have lots of clauses, they have joins which can be removed, they have some, I don't know, lots of redundancy. And for example, subplans which can be flattened. So which way you go to reduce such redundancy? Because my customers, my DBAs hate idea to introduce rules which will transform query tree before optimization. Which way you go? You simplify query tree, or you just do something during optimization, or
Yes,
maybe third way?
I mean, we try to do most during the pre-optimization and before we did go into the table order. So many of those things that you describe with lots of extra tables come from people trying to implement the anchor model, where basically you can have 10, 50 tables. You just add more tables, and you just assume that the optimizer can remove those who are not needed. So we support the anchor model, and that basically allows us to remove, quickly identify and remove tables who doesn't give anything to the result.
Okay.
So yeah, we do that, and then we just assume that the planner can handle those. As long as you have indexes, we are pretty good. The query optimizer or let's say the join optimizer who decides which order the table should be joined. If you have a lot of tables that doesn't have suitable indexes, it tries to just continue a long time to find the best table order, and that can take some time. So MariaDB works good when most table connections has some kind of index that you can use. But that's the same problem with any database. If you have two really big tables of billions of rows and you have no usable indexes, it will take time on any database.
Okay. Last question, I promise.
Wait, let's somebody else want to ask a question. We can come back to you, okay?
Okay.
All right, Pooja has a question.
Thank you, Michael, for this insightful talk. I have a question about the multi-star queries not being handled by MariaDB. So I'm curious to know what computational costs and design decisions prevent MariaDB from handling multi-star queries if there was a need for handling. Thank you.
The problem is that we basically start with one table, and then we then take the next table and join with that one, and the next table, and the next table. And the only exception is subqueries, where we then have the subqueries seen as one table. But basically, you have a line of tables. In this case, you don't have this approach doesn't work, because when you go from T1 to T2, this join may not allow us to select, basically have a where clause on T2. So we will get the whole of that in the result set. It's only when you join it with T1 that then you can reduce rows. So in this case, the best approach would be to run the current query optimizer on T1 and the linking table, and then T2 on the linking table, and then you link the results together. But we just
Thank you so much.
and the reason why we've done that is that we try to optimize things that our users and customers want. And of course, we put customer first. And during the last 20 years, we have one who asked for that one. And then they find a way to do it by just basically taking one of those, put those in the temporary table, and then join with the temporary table. So they had a solution for that. So it's not a very common thing. We have to optimize for those things that are common, that thousands or millions of people use, and not concentrate on something that only a few uses, except if they are willing to pay us handsomely for doing that.
Okay. Question in the chat.
Yes, thank you so much.
Thank you, Pooja. Question chat. Many of these optimizer functions feel like probing actual data during optimization. For OLTP, where typically queries are faster, how often are the savings found from the extra optimization based on the information that these probes are from these probes worth the extra probe cost? Typically in high concurrency OLTP workloads, I've seen database favor less optimization and work to increase throughput and reduce time taken to optimize.
Yeah, but in OLTP workload, you usually only have a couple of constants. So the problem is not there. And the constant is basically finding a constant table or finding a customer. And when you have that, everything else will be easier because you have all those in a constant. I mean, the whole customer entry is a constant. You find them instantly. The same thing with if you have a order system and you're finding a product. You know the product and you want to find all the information based on that. It's still faster to find this one row and use that as a constant. And in other cases, you don't have that many constants. So it's not a problem.
Got it. All right. One question I want to chat is, why is MariaDB moving to ARIA storage? Doesn't non-clustered indexing ARIA cause more random I/O versus the clustered indexes in InnoDB?
Okay, I didn't catch the question.
The question is, why is MariaDB moving to ARIA storage?
We are not moving. We have in InnoDB is the most used one area is for temporary tables, but you can still create the temporary table in the area.
Got it. Okay, makes sense. All right. So my last question is going to be: so is it fair to say that the big change that you guys made in MariaDB is not so much the search algorithm of the optimizer, like how you're enumerating the different choices you have, but rather it's the cost function of how you're determining whether one query plan or one choice is better than another. And you're now doing this through these more accurate sort of micro benchmarks that you developed that are that try to combine together what's the total amount of work you're going to do for a query plan. Is that a fair assessment?
Yes. And if you say that, what's the difference from MySQL? The biggest difference is that we have Oracle compatible layer, so you can take many Oracle applications and run them unchanged in MariaDB, and that's how we get most of our new business.
But that's independent of the query optimizer, right? That's like a rewrite layer in front of it.
Yeah.
And then my last question is: are you running your benchmark curl script like upon installation of a new MariaDB instance? Or are you doing this once as you build the package and then everyone's shipped with the same constants?
It's currently I did run it. I have somewhere I did write here. It's in test check costs. There's a script you can run, but we kind of noticed that the costs are still to be comparable to others. And even if you have a fastest computer and maybe not milliseconds is exact, still the difference between the cost is still pretty accurate. So it's currently we believe it's good enough. And I have a document exactly how I calculated all costs, and what I never did therefore to try to have the check cost program actually calculate all parts, because some of those was assumptions. But everything is actually documented how done, and in practice it's shown to be reasonable accurate at least 100 times better than anything we had before.
Got it. I think the IBM guys dropped off the call, but I think DB2 runs these sort of similar micro benchmarks every time you turn the thing on. It's like the BOGO MIPS in Linux. You're trying to figure out the baseline. All right, but this is super helpful. All right, again, Monty, I'm going to clap on behalf of everyone. Thank you so much for staying up late. This talk was fantastic.